Welcome friends. Again we have to discuss several variable calculus. In the previous lecture we discussed about the partial derivatives, or we can say first order partial derivatives, and we find partial derivatives of the some functions. Okay, so how we find the partial derivatives? We have to find, suppose z is equal to f of xy, then if we have to find the partial derivative fx with respect to x, then what we are doing, we are keeping y constant. That is what is the rule. Whenever we are finding a partial derivative with respect to one variable, keep other is constant. Suppose example we are taking, suppose y, or we can say that suppose f of xy is equal to, it is equal to what? X cube plus 2x square y cube. Is it? One example is there. So how we find fx? How we find? Keep y constant. Keep y constant. Fx at xy is equal to, x is what? X cube derivative is 3x square, and plus here y is constant, 2 is constant, so x square derivative is 2x, so 2 2s are 4x y cube. Okay, so we are finding fx. Similarly we can find fy. Okay, and if you see to the fx, or if you observe this, so what we are getting, this fx is again a function of it, this fx is again a function of x and y, is it? And therefore we can again take partial derivative with respect to x and y. That means what? Partial derivatives fx and fy are again functions of x and y, therefore we can again differentiate, and that means we can find higher derivatives of the function. So our today's topic is higher derivatives, higher partial derivatives. Higher partial derivatives. Okay, so higher partial derivative, suppose we have a z is equal to, suppose we have what? Z is equal to the function f of xy. Then what is the first order partial derivative? First order partial derivatives. How much we are getting? Fx, fy. Is it? Fx and fy. Then second order, how we find the, again we have to find the derivative of fx. So the derivative of fx is what? The derivative of fx xy with respect to what? X is again what? Fx x. Okay, so derivative of fx again with respect to x is fxx. Similarly derivative of fx with respect to y, what is it? It is fxy. Again what we can find? The derivative of fy at xy with respect to x is what? Fyx. Similarly what we can find? Derivative with respect to y, again with respect to y is what? Fyy. Is it? So we can differentiate again these functions fx and fy, and we are getting the second order. How much derivatives? 4 derivatives we are getting. We are getting the 4 derivatives. Again what we can see? Again this fxx, fxy, fyx, fyy, they are again functions of what? X and y. Therefore we can again differentiate. Is it? Again differentiate. So this is the fx and fy are the first order partial derivatives, and these fx, fy, fxx, fxy, fyx, fyy, these are called as the second order partial derivatives. Second order partial derivatives. And if we again differentiate this partial derivative, second order partial derivative with respect to x and y, we get a third order partial derivatives and so on and so on. So similarly we can find the partial derivatives again and again. So getting this first order partial derivatives, second order partial derivatives, and we can find a again derivative, that is one more derivative, that is fxx. We can find again, this is the third order partial derivatives. So this is nothing but the third order partial derivatives. Okay. So this one, so what are the notations, how we denote this second order partial derivatives, notation for the second order partial derivatives, notation for second order partial derivatives. Okay, if z is equal to f of xy, and then we can denote the second order partial derivatives as below. So second order partial derivative, how we denote this? This is fx x, derivative of fx with respect to x. It can be written as fxx. It can be written as what? f11, because f1 is derivative with respect to first variable, that is x. It can be written in the form of deriva by deriva x, deriva f by deriva x. Okay, derivative of deriva f by deriva x with respect to x. Again this can be written as what? This can be written as what? Deriva square f by deriva x square. Deriva square f by deriva x square, or it can be written in the form of deriva square z by deriva x square. Getting this? Similarly we can write fx, derivative of fx with respect to what? Y. With respect to y. How we write this? fxy. Is it? fx denoted by f1, fy denoted by f2. Is it? So it should be f12. It should be f12. For x it is 1, for y it is 2. This can be written deriva by deriva y with derivative of deriva by deriva f by deriva x. First we have to differentiate what it means. First what we have to what it means first differentiate with respect to x, then y. First we have to differentiate with respect to x, and then we have to differentiate with respect to y. Is it? And then what? Similarly what can we write? Deriva square f by deriva y deriva x. It is equal to what? Deriva square z by deriva x deriva y deriva x. Getting this? Similarly we can write differentiate fy with respect to x and fy with respect to y. It is nothing but fyx, it is nothing but fyy. This is f21 and it is f22, and next one is similar to above. So getting the notation of the partial derivatives, second order partial derivatives. Okay, third order partial derivatives also we can denote. Third order partial derivatives. Mostly we can write it is fxx, or we can write it is fxxy, or we can write, so first one this is we have to differentiate with respect to x with respect to y. Again this we have to differentiate x with respect to x with with respect to y. Again this, again this. So how much derivatives you are getting? 2, 4, 6 and 8. 8 derivatives you get, 8 derivative third order partial derivatives. So it may be fxx, fxyy, or it may be fyy, fyxy, and so on. So similarly you can write the third order partial derivatives also. This can be written in the form of dabba cube by dabba f dabba x cube. So you can write like this also. Okay. So these are the notation for the second and third order partial derivatives. Now we also discussed the definition of a first order partial derivatives. How we define, if z is equal to f of xy, then derivative of f with respect to x at point AB, what is the definition? Limit h tends to 0, f of x plus h, fx, or we can write it is a plus h and b minus f of ab upon h, is it? So what we did here b is constant or y is constant, that is b is constant or y is constant, and change in x only, change in x only. Okay. Similarly here also what? Fy at AB, here what we have to denote, it can be written like this, h tends to 0, here x is constant and we have to differentiate with respect to, so it should be b plus h minus f of AB upon what we can write h. Okay. And last time I also told you, that is you can take here k also, no problem, you can take k also. Okay, it is just variable, so don't worry. So can you define second order partial derivatives? Can you define a second order partial derivatives? In the similar manner you have to define again the if z is equal to f of xy, then the second order partial derivatives are defined as. So how we define this? Suppose we have to define fxx at AB, fxx at AB. So how we write this? Limit h tends to 0, is it? Then what we can take? What we have to differentiate? We have to differentiate this fx with respect to x. So you have to write here fx at a plus h and here b minus f of ab upon h. Or we can write here again fxy at ab. So how we write this? Limit h tends to 0. Now what we have to differentiate? We have to differentiate fx with respect to y. So where should be change? Where should be change? Here is fx, change in y, x is constant, so it is a b plus h minus f of ab upon what? H. Okay. Similarly you can write the definition for f x f y x at ab, and similarly you can write definition for, okay. So this is the definition, so you can write for these two. Okay, so what is the important, that is here y is constant, here we have to take derivative of fx with respect to x, that time y is constant, so change in what only? Change in x or varies x. Here varies x, this is the important. Suppose you have to take three derivatives, suppose it is fxx. How we denote this? So what should be there? What should be there? There should be fxx. Here should be fxx. And so on. That is, just keep in mind you have to take this function. And where it change, here you have to differentiate with respect to x, then y is constant. If here is we have to differentiate with respect to y, then x is constant. And keep this function as it is here. So this is the just definition of the second and third order partial derivatives. Getting this? Okay, so we can solve some problems of finding the second order partial derivatives. Okay. So here first problem is given. What is first problem? Find all second order partial derivatives of this given function f of xy is equal to x cube plus x square y cube minus 2y square. Okay, 2y square. So what should be there? What we have to find second order partial derivatives. So what it means? Are they sometime given? Find fx, fxx, fyy, fxy and fyx. Find this if this function is given. You can find. So for 1 mark this should be you have to find second order derivatives. Okay, so how we find this? So given, what is given? Write first properly function x cube plus x square y cube minus 2y square. So first what we have to find? For fx at xy, what we have to do? Keep y constant and differentiate with respect to what? With respect to x. So keep y constant. So fx at xy, it is equal to what? Here x cube, derivative of x cube is 3x square. Here y is constant, so derivative of x square is 2xy cube minus, here is what? Y is constant, so it should be 3x square plus 2xy cube. Is it? Now next what we have to find? We have to find fy first. We have to find fy. How we find? For fy we have to, again you can write for fy xy, keep x constant and differentiate with respect to what? Y. Okay, so fy xy, it is equal to, if it is equal to what? What is this? So there is a fy, so x is constant, so this is 0. So it is 3x square y square minus 2 to the 4y. So this should be 3x square y square minus 4y. Is it? Now what we have to find? We have to find fxx. Okay, so what we have to find? Fxx at xy, or we can write it is x, and what is our fx? Fx is what? 3x square plus 2xy cube. And what is the derivative? Derivative, here y is constant again, so it should be 3 to the 6x. 6x plus what? Here is y is constant, so it should be 2y cube. It should be 2y cube. Is it? So what is next? What is next? What we have to find? fxy. That is derivative of fx. Derivative of fx with respect to y. So what is our fx? Fx is 3x square plus 2xy cube. And it should be what? It should be what? So x is constant, so this is 0. So it is, what is the derivative of y cube? It is 3y, so 3 to the 6. 6x y square. So what is our answer? 6x y square. What do we have to find next? Fyx, xy. So fy means what? We have to differentiate with respect to x. So dabba by dabba x. What is our fy? What is our fy? This is 3x square y square minus 4y. So here differentiating with respect to x, so y should be constant. So 3 to the 6x y square minus 0, y is constant here. So 6x y square is our answer. Okay, similarly what we can write, f y y x y. So differentiate fy with respect to y. So this is our x fy. And how we write this? What is that? X is constant, so it should be 3 to the 6 x square y minus 4. It should be 4. Okay. So this is our first example, that is all the partial derivatives fxx, fyy, fyx and fyy. Okay. The second example. For second example, what is given? Given is fxyz is equal to sine 3x plus yz. Okay. So we have to find, and what we have to find? To find what we have to find? fxxyz at xy. Okay. So first we have to find fx, then fxx, then fxxy, and then fxxyz. Okay, it is also very important. It can be asked for 1 or 2 marks. Okay, so first what we have to do? For fx, differentiate with respect to x, keeping y and z constant. Okay, so what should be this? Fx, so derivative, this is fx at xyz, derivative of sine. You have to use here chain rule, because sine is again a function of 3x plus yz. Okay, so derivative of sine is cos 3x plus yz into deriva by deriva x 3x plus yz. Okay, so what should be this? Fx at xy z is equal to what? This is derivative of this is what? Here y and z constant, it should be 0. So derivative of 3x is 3 cos of 3x plus yz. Is it? Similarly, we can find fx xy z. How we find this? Again we have to differentiate this one with respect to x, keeping y and z constant. So it should be what? 3 is there, cos, derivative of cos is minus sine 3x plus yz, again with the help of chain rule, deriva by deriva x, here 3x plus yz. Is it? And this should be what? Again derivative is 3 3s are 9, minus 9 sine 3x plus yz. Okay. Now what we have to find? We have to differentiate this with respect to y. And for this what we do? We take derivative of fxx with respect to y, keeping x and z constant. So what should be this? fxxy at xyz, it is equal to what? Again minus 9. Again you have to use here chain rule. Sine derivative is cos, derivative of sine is cos. Okay, so here is cos of 3x plus yz into deriva by deriva y of 3x plus yz. Then what should be the answer? fxxy at xyz is equal to, okay, derivative of this with respect to y, 3x derivative is 0, yz derivative is only z. So minus 9z cos of 3x plus yz. Is it? Now what we have to find? We have to find fx xyz at xyz. fx xyz at xyz. So now we have to differentiate this thing with respect to z, keeping x and y constant. Now x and y is constant. So if you see this function, here are two functions. So you have to use the product rule. Okay. So we try to differentiate. So there keep first function is as it is, and derivative of cos of 3x plus yz is again minus sine 3x plus yz, and here into dy by x of 3x plus yz, it is what? 3x derivative is 0, yz derivative is only y. Okay. Plus what we can write? This second function is as it is, and second function as it is, that is 3x plus yz into first function derivative z is 1. First function derivative z is 1. Is it? And what we are getting now? Just try to simplify. Here minus getting plus 9z sine 3x plus yz into what? Here you can write y, 9yz sine 3x plus yz minus, and it should be is 9 cos of 3x plus yz. So in the same manner you can solve so many problems. Just check your calculation and go slowly, then you are able to solve it properly. Now if you see the example this, we find, what we find here? fxy, what we are getting here? fxy is 6xy square, and again this fyx, it is again 6xy square, both are equal. Then what we can see that in the so many function or maximum time we get a mixed partial derivatives fx and fxy and fyx. These are the mixed partial derivatives. These mixed partial derivatives are equal, and then there is a French mathematician Alexis Clairaut discover a condition on the mixed partial derivative when it is equal. So we write theorem on this, and this theorem is called as Clairaut theorem. So we discuss the statement of the Clairaut's theorem. It is important. It can be asked for give a statement of Clairaut theorem for 1 mark. So we take Clairaut theorem. So if f is a function defined on D subset of R square which contain point AB. Suppose what? First condition, suppose if fx, fy, fx, fy, fxy and fyx exist in the neighborhood of AB. Second, if fxy and fyx are continuous continuous at AB, then what we can say that the mixed partial derivatives are equal at AB. That is what we can write, fx y at AB is equal to fy x at AB. That is, if f is any function and on the domain D and point AB is in D, and fx, fy, fxy, fyx are exist in some neighborhood of AB, both partial derivative are continuous at AB, then we can say that fxy is equal to fyx. It is not for all, that is not every mixed partial derivatives are equal, but if they are continuous at that point, then we can say that they are continuous. Similarly, we can say that the Clairaut theorem holds for the third order partial derivatives also. That means what? If you take a partial derivative fxyy, then this must be equal to fyxy, this must be equal to fyyx. Is it? Provided this function is continuous at a point, at that point. Okay. So, but it is not true for each and every function. We take example on this, that is where the mixed partial derivatives are not equal. It is in the practical session. Okay. So, thank you very much.